Hi everyone, welcome to Module 5. This is part 1 of a 2-part lecture series on linear regressions. So I thought this gif of That's So Raven was funny because last week we talked about how we use regressions to predict a variable, and That's So Raven, she predicts the future. So anyways, I shouldn't have explained that, but in this 2-part series, part 1, we're going to be talking about the fundamentals of regressions. So we'll go back and review a little bit about correlations, what correlation coefficients mean, and then how we use correlations to inform regression models or equations to predict a certain dependent variable outcome. In this video, we'll also talk about the assumptions that we have to have for linear regressions in order to accept the results that we get from SPSS. And then we'll also talk about the null hypotheses and the variations of the null hypothesis that we can have for both a bivariate regression as well as a multiple regression. Part 2 will pretty much be everything that you would see in SPSS. And then hopefully that will be helpful for the activity that you'll be doing this week. So just to reiterate, last week we kind of focused on this section of our big grand scheme decision tree where we have a parametric dependent variable as well as a parametric independent variable. Now, last week we said as long as you have at least 2 continuous variables or 2 parametric variables, we could run a correlation between those variables to see how they are related to each other, right? What the strength of that relationship was as well as the direction. And now this week in regressions, it's important to actually identify which variables are your dependent variable and which variables are your independent variables. So just to recap on regressions, or recap on correlations, right, we have parametric variables, at least 2 of them. If we have 2, we're running a bivariate correlation. If we have multiple variables, we would be running a multiple correlation, which is basically just a bunch of bivariate correlations popped into a correlation matrix. The main or primary goal of correlations is to look at relationships between variables. And we had noted that we were specifically running Pearson's correlations, which result in a correlation coefficient of R that can range anywhere from -1 to +1. And we noted that the value of R, so regardless of the sign, the value of R determines the strength of the relationship. So if we had a value of 1, that was a perfect relationship. If we were between 0.7 and 1, that was considered strong. Between 0.3 and 0.7 was considered moderate. And between 0.1 and 0.3 was considered weak, with the R value of 0 indicating that there's no correlation between variables. The direction was interpreted separately from the numerical value of R, indicating the direction of the relationship. So positive values indicate a proportional relationship or direct relationship in which as one variable increases, the other one is expected to increase as well. The opposite of that would be a negative correlation, where as one variable increases, the other one decreases. So that would be an improportional or an indirect relationship. Given these 2 things, in SPSS we were able to generate p-values for each of our R correlation coefficients. It's a mouthful. And P was able to tell us if the strength and direction of our relationship between the variables was significant or not, using a 2-tailed test or a 2-tailed comparison with an alpha set at 0.05, which is kind of going to be our standard for the rest of this semester. So we have these 3 pieces of information from correlations. We identified that the null hypothesis for correlations, whether you have bivariate or multiple, is that there's no significant relationship between some variable A and some variable B. And then obviously if you get a p-value that's less than your set alpha level, in our case 0.05, we would indicate that there is a significant relationship between variable A and B, and additionally we would have to specify the strength as well as the direction. Okay. The other thing that we talked about last week that I said was coming back this week was in reference to the coefficient of determination, which we also noted as covariance. We denote this by the variable r squared, so literally just taking our Pearson correlation coefficient and squaring it. And r squared represented the common variance, which we could note as a percentage, right, of the variability that was shared between two variables. Now, this will be very prevalent in our discussion, mostly in the second half of our lecture, but r squared is very important for regressions, which we can pop over to our decision tree for regressions. And it's the same variable setup for the most part, where we've got parametric, independent and dependent variables. The goal of our test is shifting, so now we want to use a bunch of independent variables, or, well, not a bunch, it can be one or more. Use one or more independent variables, which we'll also refer to as predictors, to predict a dependent variable outcome of interest. So in regressions, it's really important that you distinguish what your independent variables are and which dependent variable you're actually trying to predict. Dependent variable and quantity will just be 1, so it's one y variable, and you could have one or more independent variables or predictors. Okay, but in any case, these are the criteria that you would have to have in order to determine if you wanted to run a regression or not. Okay. So regressions use correlation coefficients. I feel like up to this point that's kind of not a surprise anymore. And just to reiterate again, we use regressions when we want to predict the value of one variable based on a known relationship with another variable. Okay, so automatically when you see regression, think prediction. That is the biggest difference between regressions and correlations. Okay, but again, the goal is to make a linear equation using one or more independent variables that predict a single dependent variable. Now there's two different types of regressions that we can run in this class. One of them being bivariate, where we're using a single independent variable to predict a single dependent variable. Or we can have multiple regressions where we're using multiple independent variables to predict a single dependent variable. Again, in both cases, either bivariate or multiple, we're using one dependent variable, or we're trying to predict one dependent variable, but we're using multiple or single or multiple independent variables to kind of contribute to the prediction of that dependent variable. Similar to correlations, when we made a scatter plot and we put a line of best fit, and we said that the slope of that line was equal to r for the most part, we can do pretty much the same thing with regressions. The only difference is that the slope of our relationship is going to be denoted by b. And this is probably going to screw a lot of people up. For anyone who memorized y equals mx plus b, it sucks, but I'm sticking to the b notation because that's what SPSS uses. And if I used a different notation, you can't really change the default of the SPSS output, so b is kind of what we have to stick with, and you're just going to have to flip the way that you remember the equation of a line. But this line of best fit is built to do two things. The first is to ensure that the sum of the residuals equals 0. And what residuals are is it's basically a fancy term for error. So in our scatter plot, we have a line going through a bunch of dots, right? And the residual, or the amount of error that exists in our model, right, is we guesstimate where this line should actually be, assuming that we had a perfect correlation, right? And so from any random scattered dot in our plot, if we take the vertical distance from that dot to our line of best fit, that is the residual, or that is the error of our line going through our actual data. Okay, so ensuring that the sum of our residuals is as close to 0 as possible is one of the goals of generating a regression line. And then the second goal of the regression line is to minimize the sum of squared residuals, or you can also think about this as the sum of squared errors. So that's just looking at what is the predicted, what is the difference actually between what we've actually measured our dependent variable to be compared to what the model has predicted the dependent variable to be. It is important to note that outliers can have a big effect on the regression equation, and we are actually testing for outliers this week using a slightly different method than we have in the past, but making sure that we eliminate any values that could potentially invalidate or weaken the validity of our regression equation is going to be important for this week. Just so you have a visual representation of the line of best fit, again, we've got some predicted variable on our y-axis and some independent variable that we're using to predict y on the x-axis. We've created a scatter plot, and we've put a regression line through the center of the plot. Our b sub 0, which is considered the constant, or the y-intercept, it's noted as b sub 0 in SPSS, so that's what we're going to call it. But it's the y-intercept, so it's where the regression line crosses the y-axis when x is 0. So given that we have no value of x whatsoever, what is the value of y? We'll go into some more examples of this in the next lecture when we actually have tables and values to look at. The other thing I wanted to point out in here is, again, the regression line has a slope of b, which is actually noted in here as b1. Now, when we have multiple correlations, we will have multiple b variables that are not the y-intercept. So b sub 0 is always going to be the y-intercept, or the constant. B sub 1, sub 2, all the way to sub n, those are going to be slopes for individual linear relationships that are included in your regression model. Okay. And then lastly, just to visualize what the residual is, all of these little red lines, right, are indicating the vertical distance from some paired observation to the regression line, and that is representing the amount of error that we have in our model. Okay, and so again, the goal is to make sure that we're minimizing the error in both directions. So you see that we have some long, some short amounts of error on both sides of the regression line. Ideally, those should balance each other out. Okay, so that's one of our goals of when we place a regression line through a scatter plot, minimizing the amount of error that we have in both directions is a goal. Okay, so when we look at the equation of a regression line, again, it's a line, so y equals mx plus b, right? You guys are used to having y, that's the same. M is usually your slope, right? In this case, its slope is going to be b sub 1, or all the way up to b sub n. It kind of depends on how many variables or predictor variables that you have in your model. X is still going to represent some predictor variable. And then b sub 0 is similar to your b in your y equals mx plus b equation. So b sub 0, again, is always going to indicate the y-intercept. It is a constant. It does not change. Okay, so I've indicated what each of these mean down here. When you have a bivariate regression, you'll only have this part here, right? And the reason being is that you have a single independent variable that you're using to predict a single dependent variable. So that's for bivariate regression. If you have a multiple regression, however, that's when you're going to have these n subscripts, and it doesn't necessarily have to be n. If you had 3 variables, you would have up to b sub 3, x sub 3, right? So it kind of just depends. N is just the number of independent variables, kind of the last one. The ellipsis represents all of the other bx combinations that you can have for the number of predictor variables that are included in your equation. Okay, so if we're bivariate regression, we're kind of just looking at this little chunk over here. If we have a multiple regression, we just keep adding on to that little bivariate regression equation with more predictor variables and their b coefficients. Now, covariance is another thing that we should probably talk about. In regressions, it'll come up as r squared and as an r squared change, depending on how many models we have. So again, r squared is going to summarize how much of the variance is observed in the dependent variable, okay, and how much of that variance is actually due to the independent variables included in the regression model. This is a little bit different from when we were talking about coefficient of determination, because that was particularly between 2 variables. But regressions can have multiple variables that are thrown into the calculation of r squared. So instead of looking at a single relationship between 2 variables, we look at the combined r between however many variables we've got, and then we can square that and get our covariance, or r squared, for multiple independent variables and a single dependent variable. So when we interpret this, it sounds very similar to how we would interpret a coefficient of determination, in the respect that we can phrase it using a percentage, right? Or the percentage of the variance we observe in the dependent variable is due to, these independent variables. So that the wording of it is very similar to when we kind of interpreted coefficient of determination last week. But it is important to note that r squared can change for each model developed in the regression analysis, and this largely depends on the type of regression method that you use, which we will touch base on a little bit in the next lecture. And we'll definitely go over it in the activity. So that regression method is going to be different than the type of regression. So I kind of want to make that distinction while I'm thinking about it. Type of regression is either bivariate or multiple. Regression method is going to be how you actually create your model. Okay. When we notice significant changes, again, when p is less than 0.05, in the r squared value. So when we have multiple regression models that are generated from a specific regression method, the difference between each of those models usually is either a variable has been added or removed. And what we're interested in is looking at how r squared changes, or how the covariance changes from model to model. And that change in r squared is going to have its own p-value, and usually that change in r squared, if the change is significant or not, that will dictate if we keep a variable in the model or if we take it out. This brings us to the assumptions that we have for regressions. So these first 4 are actually all the same assumptions that we use for correlation. So random sampling, we need to have normal distribution with no significant outliers, which we're still keeping as greater than 3 standard deviations from the mean. we have to have at least 2 paired continuous variables, which we covered in our decision tree already. And then we also need to make sure we have a linear relationship. Namely, we have to have a linear relationship because we're using Pearson correlation coefficients to inform our regression, but also this is a linear regression that we're running. So the relationships that we build the regression off of all need to be linear. We are adding some assumptions this week, and regressions, it seems like there's a lot of assumptions. Honestly, I think this test has the most assumptions out of any other test that we cover in this class, so kind of just have to bear with it for 1 week. This is a fun word to say, but homoscedasticity or homoscedastic data is one assumption that we will have to test for in SPSS. We can easily test for it using a scatter plot. We also need to make sure we have independence of observations. We do this using the Durbin-Watson test. I'll explain that a little bit more in a couple of slides. We also have to make sure the residuals, or again, residuals is another way of saying error. We have to make sure the residuals of the regression line are approximately normally distributed. The actual regression analysis is pretty robust against non-normal errors, so we say approximately normally distributed. We don't have a really tight criteria for what is normally distributed. It's more of a visual check, and then if we notice for the most part our data look normal, then we can kind of accept this assumption, but it's not super tightly regulated in terms of criteria and if we meet or violate. The last assumption we have for regressions is we should not have any multicollinearity. Whoops. And I'll explain the definition of that term in a few slides. So we'll go through each of these orange ones one by one, just so you have an idea of what we are adding to our assumption list. Homoscedasticity or homoscedastic data is going to be looking at, or what this is looking at is the constant variance of the errors. So when we have homoscedastic data, that would be kind of the example of this upper right quadrant of our sample graphs. Generally, you see this line going through the center. And what we have plotted here is the standardized predicted value against standardized residuals. So I don't want you guys to get this scatter plot confused with if you were plotting, like an X variable to a Y variable, or an independent versus a dependent. Because most of you would say oh my god, there's no correlation, right? But these are standardized predicted values versus standardized residuals. So they don't represent the independent or dependent variables. These are actually calculated through the regression, and then we plot them to see if the residuals have a certain pattern to them. So what we want is constant variance of the errors, which means we desire to not have a pattern when we have homoscedastic data. I liked the series of graphs because it also shows how homoscedasticity and linearity can be checked together. So if we generally don't have a pattern, we've got kind of a scatter of dots above our line as well as below our line, then that indicates we have homoscedasticity as well as linearity amongst our standardized residual and predicted values. Okay, so that's why we say our assumption is met when we have minimal fanning. The other term that is used is funnels. So this would be an example of heteroscedastic data, where if we drew a regression line, you notice that the distance between dots in the line are smaller on one end of the distribution versus the other side where the residuals get larger. So that's kind of what we're referring to as a fanning effect, is that the variance becomes wider and wider as we move down the distribution. Okay, so this is something we don't really want. Nonlinearity, we've gone over examples of that last week. And then if we had both nonlinearity as well as heteroscedasticity, this bottom right quadrant would be a good representation of that. Okay. It's important that we have homoscedastic data because violation of this assumption invalidates the confidence intervals that could be calculated in SPSS, and it also decreases the validity of the significance testing that we do. So generating p-values kind of creates a toss-up if we actually should accept those p-values for what they are or not. For independence of observations, we again test this assumption using the Durbin-Watson we test independence of observations using the Durbin-Watson test, which I will say the result is going to be the coefficient D, just because it's easy to say over and over again. But basically what this is going to do, it's going to assess the correlations between errors or between residuals. It's also referred to as autocorrelations or serial correlations, which is what this image is that I found on the internet. That it refers to our independence as autocorrelations. There are these subscripts down here that you might notice, and there's actually a table that corresponds with these different coefficients, but we're not going to use that table. SPSS doesn't actually give us an exact p-value for the Durbin-Watson test, so we're kind of left to our own devices on how we interpret this statistic. We could use the table to estimate p-values, but that's another table. This class, we don't really focus that much on this assumption, so I kind of just felt like we can just use a conservative general rule of thumb to make our lives a little bit easier. Generally speaking, you want you want D, right, or the result of the Durbin-Watson test to be as close to 2 as possible, because D can range from 0 to 4. Okay, so 2 is kind of in the middle, and you can see there's this little period of space both below 2 and above 2 where you wouldn't want to reject a null. In other words, you accept the null hypothesis that says an autocorrelation does not exist, right? Or which is indicating that we've met our assumption. And there's other areas where we have more inconclusive interpretations, and then there's definite regions where we want to reject the null hypothesis, in which case we would argue that we have either a positive autocorrelation or a negative autocorrelation. Or basically we're saying we don't have independence of observations in either of these more extreme regions. So to make things simpler, we are going to say if D is less than 1, or if D is greater than 3, we have violated our assumption of independence of observations. A D less than 1 would result in a positive autocorrelation. A D greater than 3 would result in a negative autocorrelation. If you guys are interested in what positive versus negative autocorrelations are, I'm happy to discuss them with you outside of the lecture. They're not super important for us to understand for this class. The other assumption that we have to have, or one of the 4 that we've added on, is that we have to have normally distributed residuals, which we can assess with a histogram and a PP plot, which we kind of looked at the beginning of this semester. And what goes into these is they're standardized values, so z-scores, if you will, of the predicted values that we get from the regression model compared to the residuals that result from the regression model. So that's kind of what these are each indicating. When we plot them in SPSS, the standardized predicted values are going to go on the x-axis, and the standardized residual values go on the y-axis. These are just examples of what the plots look like. Actual interpretation of the plots we'll go over in the next video. For the assumptions of multicollinearity, this is something we do not want to have, and there are different types of collinearity statistics that we can run in SPSS. Multicollinearity is basically when we have two independent variables or two predictors that are strongly correlated with each other. Usually this happens when one of our independent variables is calculated using another one of our independent variables. So I've given you guys examples such as mass, which could be broken down into fat mass or fat-free mass. Right, so if we correlated fat mass with mass, we probably are likely to get a higher correlation than if we were correlating mass with another measurement. Same goes with BMI, right, because height and mass both go into the calculation of BMI. So if we were using, say, height and BMI as predictors for body fat percentage, we're likely to get some issues with multicollinearity because height goes into calculating BMI. A specific or special case of multicollinearity is known as singularity, and that's when one variable is perfectly correlated to another predictor variable, or a combination of other variables. So it doesn't just have to be one. Okay. In either case, when we generate our collinearity statistics, we assess if we have multicollinearity or not using the variance inflation factor, and then tolerance, which is basically 1 divided by the VIF. So I've indicated what our red flags are, meaning you have violated the assumption if you get a value of this type. So for VIF, if you get a value greater than 5, generally we say we've violated our assumption of or that we have multicollinearity. The same goes if we have a tolerance value less than 0.2. Again, these will make more sense when we actually have values to look at in a table. So once we've figured out what our assumptions are, we've determined that regression is the right test, we then sort out what our null hypotheses are for the main effects of our bivariate regression and for multiple regression. Okay. So generally speaking, your research question should be interested in investigating if an independent variable is a significant predictor of a dependent variable in a bivariate regression. Again, 1 IV, 1 DV. The non-directional hypothesis, or null hypothesis, for a bivariate regression is that the independent variable is not a significant predictor of the dependent variable. The research hypothesis would just be the opposite of that, saying that your independent variable is a significant predictor of the dependent variable. If we're expanding a bivariate regression to a multiple regression, we just add more independent variables. So the actual wording of it doesn't change that much. You're just saying instead of one independent variable, the IVs, right? So multiple independent variables, and you would list each one that's a part of your regression model. Right? In the null hypothesis case, we'd say that that group of independent variables are not significant predictors of the dependent variable, versus the research hypothesis, which would argue that our independent variables in our regression model are significant predictors of the dependent variable. Which independent variables are significant predictors can be determined by examining the model summary in the regression output. This is also determined by the regression method that is used. As far as statistical significance, and when we look at p-values, that'll be discussed when we actually have output tables, because I think it's a lot easier to understand when you have a value to associate an example with. Sadly, there are a lot of p-values to interpret. We have a p-value for the r-squared change. We have a p-value for each variable included in the model, which is more or less kind of what the primary goal of the regression is to see how variables contribute to the prediction of a dependent variable. And then we'll also look at p-values for the overall model fit, which is somewhat similar to our orange option or second option here. So in the next video, we'll be going over how things look in SPSS, and I'll see you there.